All right, so this first example, we look at the most basic types of examples of uh, L'Hopital's rule and how it applies most directly as a quotient. So when you have a fraction, first thing we always want to do, especially with L'Hopital's rule, is get in the habit of plugging in our limiting value here and seeing what form we get. So here we'll get 0 over 0, and that's really what we have to make sure we get, or infinity over infinity. Because if you don't get this, you cannot use L'Hopital's rule. So you always need to be verifying your form. So since we verified the form, I'm just going to go ahead and say equals, and I'm in the habit of writing a little LH for L'Hopital above the equal sign and to the left, something like this, just up above it, like a little note. Doesn't have to be this big. You can make it really small. But I do that when I use dominating terms. I write dt and then the limit. If I use L'Hopital's, I do this. And it really is just an indication, it's just a way of communicating to the reader that you're using L'Hopital's rule. Because sure, it should be fairly obvious to the reader what you're doing, but it's not always obvious. So more information is better than less. So using L'Hopital's rule, we'll take the derivative. And then at this point, we want to see, do we get another indeterminate form? Because sometimes one application of L'Hopital's rule is not necessarily sufficient to clear the indeterminate form. So if we go off to the side here, secant of 0 is 1. 1 squared is 1. So we get 1 plus 1 over cosine of 0 is 1. So we get 2 over 1, which is 2. So this is not indeterminate. We were actually done. That's the answer. But each time you perform L'Hopital's rule, you want to reassess the form. Sometimes you'll have a problem that requires multiple applications of L'Hopital's rule. Over here, let's plug in. We're going to get infinity over infinity. And then we can go ahead and use our L'Hopital's rule. So ratio of the derivatives, e to the w, 3w squared. Again, the form stays infinity over infinity. So we do another application of L'Hopital's rule. And yet again, we do another application of L'Hopital's rule, because we still have infinity over infinity. And finally, at this stage, we will have successfully cleared that indeterminate form. We have e to the w over 6, and if we just evaluate this e to the w goes to infinity, and dividing by 6 doesn't change anything there, so this is just infinity. Now there's this pattern, this trend with L'Hopital's rule that usually you can decide what's going to be a better method to use. This is not a great one to use L'Hopital's rule on because, look, of all that work we had to do. We will talk about this later in the section, but you all should, to one degree or another, have the sense that exponential growth is faster than any polynomial growth in the long run. Sure, a particular polynomial might grow faster than than an exponential would for a little bit of time. All right, you might have a really high degree polynomial, and maybe it does something like this. And e to the x does something like this. So sure, it looks like this polynomial is outgrowing the exponential. And that'll be true for a while, but eventually this exponential growth will outpace this polynomial eventually. Maybe you have to look at x equals 1,000 before the exponential overtakes the polynomial. But eventually it will. Exponential growth is faster than any degree polynomial growth in the long run. So in other words, it might not, for any particular finite length, it might not be winning, but in the long run, after a long enough time, if you wait, it will overtake and outpace the polynomial. So in that case, we could have just used dominating terms. We could have just said by the method of dominating terms, this limit, well, actually, we don't even have to say that. We can just say by dominating terms, this is going to be a higher, faster growing, dominating term. So this is really just the limit. Actually, we can just say infinity. We can just say this goes right to infinity. There's no intermediate step if we use dominating terms. This outgrows that. So the answer is infinity.